distillation. So in the first half of this class, you guys learn from Ajahn Pairat about like simple binary distillation, right? So in my part, in the second half, we start with the multi-component when you have more than two components in your system. So yeah, so basically like this example right here, we have four. Okay, we have four components in the system. So the first step is to identify which one is high key, which one is light key, which one is sorry, not high key, heavy key. I'm sorry. Which one is heavy key, which one is light key, and which one is non-heavy key, and which one is heavy non-key, and which one is light non-key. Okay. So that's the first step that you should identify. And to do that, basically you have to rank their volatilities. You know, like the one that easiest to evaporate, the one that is the lightest will come out at the top, and the heavier ones will come out at the bottom. So we have so in any distillation system we have two key compounds, right? The first one will be light key, the compound that we wanted to leave at the top, and then we have heavy key, the compound that will leave in the bottom. Okay, and other compounds will be non-key. Okay, whether it's light non-key leaving the top or heavy non-key leaving the bottom. So again, the first step is to identify all the compounds, identify whether or not they are light key, heavy key, light non-key, or heavy non-key. Okay, and after that, we will do the overall balance. You know, like overall, do the overall balance of the system to find the compositions in the bottom and the compositions in the distillate. And to do that, one of the most basic assumption is to assume that all the light non-key will go to the top, and there is no light non-key going to the bottom. Okay, and another assumption is to say that all the heavy non-key goes to the bottom, and there is no heavy non-keys going to the top. Okay, so it's a complete split, complete separation of the non-keys. Okay, that's one of the basic assumption, which is usually not true in real application. And if you want like more accurate calculation, you should not assume this. But as the first estimate, as the first approximation, you can assume that all the heavy non-key goes to the bottom and all the light non-key goes to the top. Okay, so this example right here use that principle, that assumption, do the overall balance calculation and solve for the compositions in the bottom and in the distillate. Okay. And next is the stage by stage calculation. Okay. So in addition to like the overall balance, we also interested in each stage. Like we want to know the compositions in each stage. Okay, so what we do is we can either start from the top to the bottom, or the bottom to the top, up to you. Okay, so like right here, we start from top to the bottom. Okay, so the key point is to hold on a second. Like the key point is to switch, between the equilibrium calculation and the equilibrium equation and the ovulating equation. Okay, so if we start from the top to the bottom, we will use this equation here, which is the dew point calculation. This is the equilibrium. Okay, equilibrium equation, and then we switch to the ovulating equation right here. These two right here. Okay, these are the ovulating equations, and this one is for the enriching. This one right here. This one right here is for the enriching, and the lower one is for the stripping. Okay, and you have to switch. I think the one of the tricky part is to know when to switch. You know, like when to switch from enriching ovulating equation to stripping ovulating equation. Okay, you switch it like like above the stages above the feed. We'll use the enriching ovulating equation, and then the stages below the stripping equation. We'll use the stripping ovulating equation. Okay, so as I said here, you have to calculate switch from x to y, y to x to y to x to y to x. Switching between the equilibrium and the ovulating equations. Okay, until you reach this requirement here, when your calculated composition of heavy key at stage n+1 is greater than the specified heavy key composition in the bottom, and also to meet the requirement of when the composition of light key at n+1 is less than the light key composition in the bottom that's specified by the problem. Okay, and then you stop your calculations, and this n+1 right here is the number of stages. N+1 is the number of stages in the column plus the one stage in the partial reboiler. Okay, so you have to be careful again here with the n+1. Okay, n+1 is okay. Let me write it down. Number of stages plus partial reboiler. Okay, number of stages in column. Okay, so yeah, so when you answer the problem, make sure that you say clearly whether that number is just the number of stages in the column or like every equilibrium context, which also include the partial reboiler. Okay, so be careful of the number that you answer. Okay. And then after you determine the number of stages, then you would want to find the optimum feed stage. Like which feed stage gives you the best result. And to do that, you have to do a bit of trial and error here. Okay, so you have to first randomly pick one feed stage and use that feed stage to calculate, to find the total number of stages. Okay, and then try different feed plate locations. Try different locations of the feed, and to see which feed location gives you the lowest, the minimum number of stages, and that one would be your final answer. Okay, the best condition with the best location for the feed and the lowest number of stages. Okay, so that's how you find the feed location. And then next, this one right here is a bit, this one is probably one of the more difficult session in this class is to correct the initial assumption. Okay, as I said before, when we do the calculation, we assume that it's a complete splitting, right? It's a complete separation of the non-key components. We assume that all the heavy non-keys go to the bottom and all the light non-keys go to the top. But that's just an assumption. It's not quite true in the more accurate calculation. So to correct this assumption, you have to follow these steps here. Okay. I'm not gonna go into much detail. So basically, you have to redo the calculation again and again until you get the error that is less than the acceptable error epsilon. Okay. You try again and again until you get the error lower than the acceptable error epsilon. Okay. To counter the assumption of the complete splitting, okay, to find the true fractional recovery of non-keys. Okay, so in the initial, let me say it again. So in the initial assumption, we say that heavy non-key is 100% recover in the bottom, right? And light non-keys is 100% recover in the top, in the display. But that's not true. We have to find the true recovery fractions of the heavy non-key in the bottom and the light non-key in the top, in the display. Okay, so to do that, you have to follow these steps here. Okay. And this slide here. So before I said that we start the calculation from the top to the bottom, right? That is when that procedure is appropriate when your light non-key, when you only have light non-key in the system and you don't have heavy non-key. Okay. So but in contrast, if in your system you have like heavy non-key but not light non-key, then maybe you can start the calculation from the bottom up to the top instead. Okay, and this one will use the bubble point calculation, but the concept is still quite similar. Okay, so you have to switch between equilibrium equation and the ovulating equation, and you have to switch from stripping ovulating equation to the enriching stripping. Sorry, let me say it again. So you have to know where to switch from stripping ovulating equation to the enriching ovulating equation. Okay, when you move from below feed stage to the above feed stage. Okay, that is when you have to switch the ovulating equation. Okay, so yeah, but the concept is still similar to before. Like you have to keep doing the calculation stage by stage, changing from equilibrium to ovulating to equilibrium to ovulating to equilibrium to ovulating. Okay, so that's what you do. And yeah, this profile just to show you like what's going on inside the columns. Okay, so that's pretty much for chapter 5. You guys have any particular question? Any question at all? Are you guys still with me? No question? Okay. So quite simple. So yeah, let me go over the exercise quickly a little bit. So yeah, in these two problems, so the first question just to ask you to find the compositions in the display and in the bottom. So this one you can use like the overall balance equation, assuming the complete splitting. Like assuming that all the light non-keys go to the display and all the heavy non-key goes to the bottoms, and do the balance things, and then this is what you get. And then for the second problem, this one is to do stage by stage, to do the stage by stage calculation, because the question asks for the total number of stages required, and also to find the feed location. Okay, so this is what I do, and you guys probably already saved this. So yeah, I started with my first case when I picked stage two to be my feed stage, and then I keep doing the calculation, and I switch. I switch. So I switch the oblique equation from the enriching one to the stripping one when I go, from one stage, from above feed stage to below feed stage. Okay. Yeah, keep doing it until I got the number of stages to be 4.82. Okay, I did some interpolation here just to be exact. Okay, and then my second case is to use feed stage to be stage 3, and I got 4.63, and then my third case is to assume the feed stage to be at stage 4, and then I got the answer to be 4.88. So from this, it seems that my second case, when I say that the feed stage is at stage 3, give me the best result. So this is my final answer. Like the total number of stages is about 4 to 5 stages, with the base location for the feed stage to be at stage 3. Okay. So that is that for chapter 5. Okay. No question. Simple. That like this one, you just need to be careful with the calculations, and of course, it would be best to use Excel, right? To use Excel would be best for doing this kind of calculations. And then chapter 6. So for chapter 6, so basically is like it continues from chapter 5. We're still dealing with multi-component distillation, but in chapter 5, it's kind of time consuming, right? It's a bit time consuming to do stage by stage calculation. So that's why there are some shortcut techniques, shortcut methods for solving the multi-component distillation, and we use Fenske equation and Underwood equation, okay, to solve this. So for the first one would be we use the Fenske equation with the system when you have the total reflux. Okay, so for the total reflux system, it means that there is no distillate coming out. There's no bottom coming out. So like all the compounds being circulated in the system, like to get the maximum interaction between liquid and vapor phase. Like when you have like when you just keep like you just have the streams keep getting in contact with each other to be in equilibrium as much as possible. So this way, when you use the total reflux, you will require the lowest number of stages. Okay, so in this case, you for the Fenske equation, you're gonna get like the minimum number of stages theoretically possible. Okay, so because of course in real application we don't use total reflux. Like we want to get something out of the column, right? We want to get this way, we want to get bottom, but in this theoretical situation, we assume the total reflux to get the lowest number of stages possible for the total reflux. And okay, I'm degree. So this is one of the form. Okay, so this is one of the form for the Fensky equation. Okay. Oh, or you can use this form here, or you can use this form here. It depends on what information the problems give you. Okay, so usually it will be this form, because the problem usually give us like the fractional recovery of the key components. So we can use this form to solve the minimum number of stages. Okay. And once you know, like the minimum number of stages, you can rearrange the Fensky equation and to solve for the fractional recovery of other non-keys. Like for example, in this case, when in this column they have C, compound C as a non-key. So after they calculate and get the minimum number of stages, then then you rearrange the Fensky equation into this form right here, and then you can solve for fractional recovery. Okay. And you can write many other forms. It's basically just like rearrange. You need to know how to rearrange this form. Okay, like how to rearrange this form into other compounds, and then you can find fractional recoveries of like non-keys. Go quickly. Yeah, like for example here, so the problem asks for the minimum number of stages. So just plug in the values, and then the question also asks for the fractional recovery of the light non-key C, compound C, and this is what we get. And then another sorry, you guys can hear me, right? I got myself kicked out a little bit. Okay. Okay, sorry. I don't know what's wrong. Okay, but anyway, I try again. So I just finished mentioning about Fensky equation, and the Fensky equation is for the total reflux system. The total reflux system gives you the minimum number of stages, the lowest possible, the lowest theoretically possible, and then we move on to another case. Okay, we move on to this case here when in the opposite situation, in another extreme, when you use the minimum reflux. Okay, so in this case, when you use the lowest reflux possible, you're gonna get the infinite number of stages. Okay, so in this case, it's the opposite of before situation. So this time we want to use minimum reflux, and you will get the infinite number of stages. Okay, and in this case, we consider the Underwood equations. Okay, and then so I'm just gonna write to the equation that we're going to use. Yeah, so the Underwood equations, okay, so these are two Underwood equations that we use. Okay, so the first Underwood, we use it to find the free value. Okay, and then the second Underwood, we use it to find V minimum. Okay, so that once we know V minimum, then you can find L minimum and then find the minimum reflux ratio. Okay. And there are three cases of using the Underwood equations. So the first one, when probably the simplest case, when we assume that when we assume the complete separation of the light non-key and heavy non-keys. Okay, so in this case we assume that all the light non-keys go to the distillate and all the heavy non-keys go to the bottom, and then we use the first Underwood. Okay, we use the first Underwood to find the free value. Okay, and then once you know the free value, then you use the second Underwood to find V minimum, and then you find L minimum, and then you can find the reflux ratio V over L or L over V, up to you. Okay, so yeah, that's L over V, yeah, L over V, the reflux ratio. Okay, and then this is case one, and then case two is when you don't assume the complete separation, but you use Fenske equation. You know, you use Fenske equation along with the Underwood equation together. Okay, so in this case number two, you don't assume the complete separation of light non-key and heavy non-key. You use Fenske equation to find, you know, like the x and k, okay, in this way, and then you use the first Underwood to find phi, and then kind of similar to okay, and then you find, yeah, the xlk, the xhk, and then use second Underwood to find v min, and then do the same as case one. Okay, so the difference between case two and case one is that case two, you use Fenske equation. Case one, you don't use Fenske equation, and in case two, you don't assume complete separation of the non-keys. But in case one, you assume the complete separation of light non-key and heavy non-key. Okay. And then case three, this one when you have like multiple compounds, and you are you know, like you are interested in finding all the free values between the compounds, then you use this technique here. Okay, so this case three is probably a little more complex than the previous cases. Yeah, go a bit quickly here. So then, like for example, in this case, they have three compounds. No, sorry. Yeah, maybe they have three compounds, A, B, and C. Yes, they have three compounds, A, B, and C. So this one, right here. Hold on a second. Yeah, they use information from 6.1. Okay, and in 6.1, this 6.1 here is when we use the Fenske equation, we don't assume complete separation, right? We get like 99.8% recovery of light non-key C in the distillate. Okay, so in this problem, we don't just assume that the line non-key 100% recover in this rate. We actually find the true recovery percentages, and we got 99.8% for the line non-key. Okay, so and then in example 6.2, so basically example 6.2 is fits case 2 here. Okay, it fits case 2 when you don't assume the complete separation. We use the result from 6.1. We use the result from the Fenske equation. Okay, we use the result from Fenske equation and then continue with the Underwood equation here to solve for phi. Okay, to solve for phi, and then all of these, and then and then use the second Underwood to find V min, and finally I find the minimum reflux ratio here. Okay. So this one kind of fits case number 2. Okay, case 2 here. Okay, so once you guys finish with Fenske equation to finding the minimum number of stages, and finish with Underwood equation to find the minimum reflux ratio, and then you can use like this plot right here, Gilliland correlation, to find the actual n and the actual the actual L over D, the problem should specify for you. But like to find the actual n, you can use this Gilliland correlation plot to find n. Okay, using the minimum number of stages and the minimum reflux ratio that we calculated from Fenske and from Underwood equations. Use those information to find the actual n. Okay. Or if you don't like the chart, don't like the graph, then you can use like these equations here. These equations actually fit. They are like fitting equation, the equations that fit the graph from before. Okay, so you can do that. And then also you can find the feed location by using this form of Fenske equation to find the feed location for the minimum number of stages. Okay. When you use the minimum number of stages, you use the Fenske equations, and you can find NF minimum here. And then we assume that the ratio, the ratio between NF to N is the same, whether or not it's at the minimum number of stages or the normal number of stages, the actual number of stages. Like we assume that the ratio is the same, so you can use this ratio to find the actual NF to use. Okay. And this is example here. So continuing from example 6.1 and 6.2. So we find minimum reflux ratio, and we find n minimum. Okay, so using the chart, you can get the actual n. Okay, the actual number of stages, and also you use this equation to find NF minimum, and then use this ratio relationship to find the actual NF. Okay, so so that's the main point of chapter 6 is to use Fenske equation and Underwood equations as a quick shortcut methods. Sorry, I get. let me check something. Like I keep getting okay. Okay, so that's for chapter 6. Anyone has any question here? Anyone still with me? And I think one of the trickiest part is to find the free value. Okay, this is important here. Okay, like for example in this case, okay, the fee to find the free value probably one of the trickiest part because usually you would use like your calculator or Excel to solve a fee, right? You it's kind of it's kind of difficult to solve the equation by hand. So you usually use like calculator or Excel, like goal seeker function to solve for free. But you have to make sure that the fee is the value is between the alpha. Hold on a second. The light key is greater heavy key. Okay. But you have to make sure that like the free value is between alpha of heavy key and alpha of light key. Okay, so this is important here. You cannot just like believe whatever value the calculator gives you. Okay, so you have to be careful here. Probably this is like one of the difficult part because when you solve for the equations, like for example like these equations right here, you can have like multiple roots, multiple answers, right? Like you can have multiple answer, multiple roots. That's simple. Like for these like polynomial equations. So, but not all of the rules, not all of the answers can be used. Okay, only one like this. Like the value with the value between alpha of heavy key and alpha of light key. Okay, so you have to be careful here when you solve for phi. This is probably like the trickiest part. Okay. And no question at all. Anyone? No question. So yeah, let me go over the exercise again. Chapter 6. Okay, so for chapter 6, chapter 6 exercises. Okay, so like for example, in this problem, this one is for question 1, it just this one is a binary distillation. They only have like light key and heavy key in the system, and yeah, the question just asks for the minimum number of stages, and yeah, so we solve that using the French-K equation. Yeah, like use French-K equation, and then the question asks for the minimum defect ratio. So to do that, we use the Underwood equations to solve for phi. Okay, to solve for phi, and then yeah, use the second Underwood equations. Yeah, then solve for minimum defect ratio here, and then to find the actual n, we use the Gilliland correlation to solve for n, the actual number of stages. Okay. And next is the second question. So for this second question, they have 4 compounds. Okay, so for 4 compounds, so first I use the Fresnel equations to find the minimum number of stages, and also to find the actual fractional recovery of light non-key and the heavy non-key. Okay, so using Fresnel equations, I solve for this. Okay, and then after that, I can calculate all the compositions in the distillate and all composition in the bottoms. Okay, and then from this, I can calculate NF minimum. Okay, and then I use the Fresnel the Underwood equation to solve for phi. Use Fresnel equation to solve for phi, and then I can solve for L over D minimum here. And then yeah, I use this. I didn't exactly use the Gilliland chart. I used the fitting equation and to solve for solve for x, and then from x I can like solve for the actual number of stages, and then use this ratio relationship to find the free location, which is 18. Okay, so any question at all? You guys still with me? No? No question at all? We have, again, like we have exams, final exam in 2 weeks. I don't know, have you guys like review at all, like the materials, but you guys, like, I suppose you guys have questions, but like you guys still waiting for that chapter to ask. I guess like chapter 5 and 6 still kind of simple, so that's why you have no questions. Okay, so no question. I'm just gonna move on to chapter 7 then. I forgot to remove all the. Okay, so next, batch distillation. Okay, so in our previous calculations, you guys have to deal with continuous. Okay, you guys have to deal with continuous systems. But for this one, it's batch distillation when there is no continuous flow. When you put all the feed into the system and wait for it to operate until you stop the process. Okay, so the process doesn't doesn't operate continuously, but only work batch by batch. Okay, and to do batch distillation, we use something called Lele equation. Lele equation to solve for the batch distillation. So this form right here. Okay, so you have to use this form to solve for batch distillation, because like these variables, like depend on time. Even though you don't see any time, any time variable in the equations, but like these variables they all change with time. Okay. Anyway, yeah. So we use the Lele equation with the batch distillation. So in the case of simple batch, so it's gonna look something like this. Okay, when you basically you just have a pot, like you have a pot, and then you just put all the feed into the pot and heat it up, and try to condense and capture the distillate, okay, to get the product that you want. Yeah, so just follow these steps here. So first you have to plot the XY equilibrium, and then plot the 1 over y minus x versus x. Make this into plot, and then we make this plot because we want to solve this integral, right? To solve this integral, when one of the simplest ways is to make a plot and find the area under the curve. Okay, finding the area under the curve is one of the simple technique to solve the integral. Or if your equation is easy enough to solve by integral, then you then go ahead. You can solve the equation analytically by solving the equation, or you can try to use like the numerical technique. Okay, but yeah, we don't talk much about it here. But you can also use like numerical technique to solve for the integral. Okay, so like in this case, we kind of focus on like finding the area under the curve method, and then from this, you can solve for W final, and then you can solve for XD average and D total using these mass balances here. Okay. But okay, so in the case when your relative volatility is constant, okay, and then you have binary, okay, and binary, okay. When your alpha is constant and your system is binary, when you only have two compounds, then you can kind of use this equation here. Like you can like do the integral, like solve the integral analytically and derive this equation. Okay, so this form you can just like plug in the value. But again, be careful. This one is only for binary simple. Simple batch. Okay, simple batch. No column or anything. Okay. Only binary simple batch. Then you can use this equation here. Yeah, just like this example here. You should have the x and y equilibrium data, and then you find this column right here, 1 over y minus x, and make the plot of 1 over y minus x versus x. Like make this plot, and then find the area under the curve, and then you can just use like the equations that we talked about before to solve for D and XD. Okay, but in this problem right here, the problem doesn't give you the XW final. Okay, so you have to guess. Like in this problem, the problem doesn't give you XW final, so you have to guess. Like try different guesses until you get XD to be the same as what the problem gives us. Okay, the problem gives us XD to be 0.892. So yeah, you just need to get XW final until you get XD to to be as close as possible to what the value the problem gives us. Okay, and next is the constant level batch. Okay, this one is a special case. Is when you want to switch the solvent. Okay, this technique is used when you want to switch the solvent. Like for example, you have like originally you have compound A dissolved in solvent B, but you want to dissolve A in C instead, in solvent C instead, B, and replace it with solvent C. And the way you do it is, like by trying to boiling off the solvent B, the original solvent B, but also keep adding, continuously adding the second solvent C to replace it. Okay, so by doing that is called constant level batch distillation, and you use like this equation here to solve for the constant level batch distillation. And next is the multi-stage batch. Okay, so multi-stage batch. So basically, you have like a pot and also a column on top of the pot here. Okay. So yeah, so this is gonna be multi-stage batch. Okay, so you have a column on top of the batch. And there are two modes of operation: constant refract ratio and the variable refract ratio. Okay, so there are two modes of doing this. So the first mode is constant refract ratio. This one, you're gonna have like multiple lines of operating equations. Okay, you have multiple lines of operating equation, but each operating line has the same slope. Okay, because the slope is the refract ratio. So each line has the same slope. The difference is xd. Okay, xd is they're gonna be different. Okay, like the intersection between the operating line and the equilibrium line. Okay, so in this case we guess different value of xd to get multiple operating lines and to get multiple values of xw, so that in the end you can make a plot of 1 over xd minus xw versus xw, so that you can find the area under the curve. Okay, find the area under the curve means to find the value of this integral right here. Okay, so making a plot of 1 over xd minus xw versus xw, find the area under the curve, and then at the end of the curve between xw final and xf, and then once you find it, then you can calculate for w final and xd and d total. Okay, so this is how you do the calculation for the constant refract ratio. Okay, like this example right here, like you have two columns. Okay, two columns on top of the pot, and you like make a graph of 1 over xd minus xw versus xw and find this area under the curve. Okay, and then you can solve for w final, solve for d, solve for xd average. Okay, and then next, variable refract ratio. So in this case, you're gonna have multiple. You can have multiple operating lines, but you will have like all the lines will have the same intersection at xd. Okay, but they're gonna have different slopes. Okay, so basically you just try and guess different slopes, until it gives you until you get xw equal to xw final. Okay, so this one is opposite to the previous case. This one you fix xd, but you change the slope instead by moving the overlapping line until you get xw to be equal to xw final. Okay, and that the slope that gives you this xw final, then that slope is the final L over V. Okay, so at time equal to 0, you're gonna have L over V initial, right? And then when t equal to t final, then you're gonna get L over V final. Okay. So at the beginning, you get L over V initial, and then but at the end, when you finish the process, the slope L over V will be L over V final, and then you can calculate W final. Uh, any question? No. Okay, so chapter 7 exercises. Yeah, let me go over quickly. So this first one right here, just to find YD average or XD average, find the total. Yeah, so just make the graph, make this graph on the right here, and then find the area under the curve. And this one, you have the column. I think it's two columns on top of the pot, and it's a constant refract ratio problem. Okay, so yeah, I made these lines to get to draw to draw this graph here to find the area under the curve, and then get the answer. And then the last question, this one is the variable refract ratio. So I got two overlapping lines here. The blue line is the blue line is the final stage. The yellow line, no, sorry, the blue line is for the initial stage. The blue line is for the initial stage is and you get xw to be xf. Like at the beginning, the composition in the pot is xf, right? But then at the end, at time final, then it's gonna be yellow line right here. So this is the xw final. And xw final here. Okay, so this one example is for variable refract ratio. Anyone, anything, any complaint, any comment, any questions? Okay. Moving on, chapter 8. Okay, absorption and stripping. Okay, so absorption stripping. So again, absorption. Both absorption stripping, you have like counter streams of gas and liquid. Okay, and you want to transfer the solute from one phase to another. Okay, transfer from one phase to another. So for in the absorption, you want the solute to transfer from gas to the liquid. In the stripping, you want the solute to transfer from liquid to the gas. Okay, and usually in real plant, the absorber and stripper they go together. Okay, to reuse the solvent, to save cost and good for environment. And we use Henry's law. We use Henry law's constant for the basic calculation. We use McCabe-Thiele. So the main point is that for the absorption, the ovulating line is on top. Like for the absorption, oblique line is on top, and the equilibrium line is below. Okay, and for the absorption, you can get L over V minimum. Okay, when the slope is smallest, it can go. Okay, so this line gives you the smallest slope is the minimum L over V. Okay, minimum L over V. This is when you do the absorption. And then for stripping, it's gonna be the opposite. For stripping, the equilibrium is gonna be on top, and the ovulating line is gonna be below. Okay, the ovulating line is below the equilibrium line for the stripping. And for the stripping, you can have LOV maximum. Okay, for the stripping, you can get the LOV maximum opposite to the absorption. And you can use McCabe-Thiele. You can use McCabe-Thiele to solve the problem, like doing graphical technique. Or you can use Kremser equations. You can also use Kremser equations. But Kremser equations is only worked when the equilibrium line is straight. Okay, it's a straight line. Only works doing this. Okay, when the equilibrium line is straight. When you use Kremser equations. And the Kremser equations only give you kind of like the overall the overall information. Like the Kremser equation does give you information about stages between. Okay, like in the McCabe-Thiele graphical technique, when you draw the lines, when you draw the graph, you can see the compositions in the stages between top and bottom, right? You know some information in the stages between. But in Kremser, it doesn't tell you anything about like the stage in between. Only tell you like composition at the top or the bottom in the display or in the bottom. Like it doesn't tell you anything about like the values in the stages between. So yeah, keep that in mind. Yeah, all these equations basically just pick the right equations for the information that given by the problem. Okay, look at the problem and see what kind of information the problem gives you, and then use the right equation to solve the problem. Okay, and this is kind of quick, and you can also kind of like estimate the column efficiency by using this graph right here. And in the case when you just don't have only a solute. Okay, sometimes you have multiple solute in your system that transfer between one phase to another. Then the way to do it is you have to make sure that your system is dilute. When it's dilute, it means that first you have to assume that your system is dilute, and also assume that all the solutes they ignore each other, they don't interact with each other. Like the equilibrium of one solute doesn't depend on other solutes. Okay, that way you can solve the problem one solute at a time. Okay, so just like this graph right here, like they have three solutes here. So they start with the solute that they care the most about. Maybe like in this case is compound B. So they start with compound B and do the calculation for compound B to find the number of stages, and then use that number of stages to solve for other solutes. Okay, so in this case you can solve the problem one solute at a time. Just assume that they don't care, they don't interact with each other. Okay, so that's how you do it. Yeah, that's absorption stripping. And next, chapter 8, right? Chapter 8 exercise. I don't know. Yeah, the first one is the absorption. Yeah, I use the graphical technique and get the number of stages. And the second one is just example of stripping. So for the stripping, the operating line is below, and the equilibrium line is above. And then the third question is the multi-component. So I have two solutes here. So I start with the calculation for the first solute, the methane, and then I move on to the next solute, which is the argon. Yeah, so do the calculation one solute at a time. Okay. And then chapter 9. Yeah, I go